Assalamu alaikum dear students, we're back with another video lesson. In the previous video lesson we were talking about photoelectric effect, and of course we said photoelectric effect it is a phenomenon that it happens when photons emit, or let's say incidents or fall on the surface of a metal, electrons will be ejected. And of course we said that there were different, of course you can say, saying about this between, let's say, classical and of course let's say between the experimental results. And classical said that any frequency, let's say any light with sufficient energy should be able to extract electrons from the surface, but of course you can say experiments showed that the otherwise. They said that only certain frequencies are able, let's say, to extract these electrons. And of course following with other points that of course let's say that they said if the energy that is incident, let's say if it is not enough, then of course it will take some time and then afterwards electrons will be ejected. They also said that let's say the kinetic energy or maximum kinetic energy of these electrons would depend or depends on the light intensity. But on the other hand, we said the experimental data showed that only certain frequencies are able to, if, or you can say if the incident frequency is bigger than the threshold frequency, then of course electrons will be extracted from the surface of the metal. And so it doesn't matter, for example, or let's say it does not depend on the intensity of, you can say intensity of the incident light or incident energy there. And we also said that once electrons are extracted, then of course increasing or doubling the intensity, then it would double the number of the electrons that are extracted. And we also said that the kinetic energy of the particles will not depend on the intensity, but rather it depends on the frequency of the incident light or incident energy, you can say. And of course then we ended up, and after that we talked about, let's say, what was the other thing that we were talking about. And of course we saw, or we kind of like mentioned the difference between classical and of course you can say the experimental as well. And then we ended up right at this point here. So now we have threshold frequency depends on the work function of the surface here. So we're still talking about photoelectric effect here, but now we're talking about, didn't we mention that there's a certain frequency, if the frequency of the incident light or energy, let's say, or whatever the electromagnetic wave is, let's say if that frequency of the incident energy, if it is equal to or above the threshold frequency, then of course it will be able to extract electrons. But if it is below the threshold frequency, then that energy will not be able to extract, or that wave will not be that photon we can call it, or energy, or you can call it a wave, whatever you like to call it, will not be able to extract electrons from the surface of that metal here. So what is the work function we can say? So we can start with this. To eject an electron from a metal surface, you can say it must overcome the work function. So what is work function? Of course, we'll get into a point now, which is equal to Planck's constant times the threshold frequency, which is basically, so the work function, we can say it is the minimum energy required for electrons to be extracted. So once again, if you want to eject electrons from the surface of the metal, then of course the energy of the incident wave must be bigger than, or at least, let's say, if it is at least equal to or bigger than the work function. Now we'll talk about this difference, for example, why sometimes we say if it is bigger, sometimes we say if it is equal or bigger than that. Okay, so the work function, so what does the work function it is equal to? The work function, we can say it is equal to Planck's constant times the threshold frequency. And of course, where F is the threshold frequency, or you can say for the metal, that is the frequency, for example, that we compare with the frequency of the incident, let's say, energy here. So photons with energies, watch this, photons with energies greater than, watch this, greater than the threshold frequency are able to eject electrons from the surface of the metal. I know that you want to ask, what if it is not greater than? What if it is equal to? I'll answer that question in a second. So we'll say the maximum kinetic energy of the ejected electron, remember this, the maximum energy of the ejected electrons will be the difference between what? Between the, let's say, between the photon or the energy that falls on the surface of the metal and of course the threshold frequency or the work function. That would be best if we say that one here. So once again, didn't we say that the kinetic energy of the or maximum kinetic energy of the emitted electrons depends on the frequency, that is exactly what we mean by this. So we can say that the maximum kinetic energy of the ejected electrons depends on, or you can say it is the difference between the photon energy and the work function, you can say, for that metal. So by the way, one more thing, remember this, the work function, it is not one thing or it is a fixed thing for all the materials. No, every single material or object, let's say, material would have a different work function because they have a different threshold frequency. So we cannot say if of a certain frequency that can eject electrons from one metal, can we say that any type of frequency, let's say using that frequency, will it eject electrons from the surface of any other metals? The answer is no, because every metal has their own threshold frequency, which you can say their own work function. Okay, so now if that is the work function, how we can define work function? We said work function is equal to, remember, we have energy that is equal to h, Planck's constant, times frequency. Work function, it is equal to Planck's constant multiplied by, or you could just say threshold frequency there. Okay, or if not, we could just use this one. Sometimes we use this symbol for work function as well. If not, you could just write work function. Okay, work function, it is equal to what? It is equal to Planck's constant times, of course, threshold frequency here. Okay, so that is for that here. Now, so we can say, or how do we define work function? We'll say it is the minimum energy needed to remove an electron from a metal surface, you can say, or you could just say from a metal there. So once again, what is work function? It is the minimum amount of energy that is required to eject, to remove an electron from the metal surface here. Okay, now we have something else. What about Einstein's equation for photoelectricity, or you can say for photoelectricity, or photoelectric, you can say, and of course, maximum kinetic energy of photoelectron as well. So we said that work function, it is equal to Planck's constant times threshold frequency, yeah? And of course, we also said that the maximum kinetic energy, it is equal to the difference between the energy of the photon and the work function here. So based on that, of course, we're going to write this one here. We'll say maximum kinetic energy here, maximum kinetic energy, that is maximum, we said that is equal to the difference between what? The difference between the energy of the photon and the work function. We say work function is basically HF naught, you can say, yeah? So, but we do know that the energy, that is basically of the photon, it is equal to h Planck's constant times the frequency of the incident wave, you can say, or energy, and that is minus h f naught here. So this is basically what maximum kinetic energy is. Sometimes you will be asked to find the work function, then of course you will take the work function given the maximum kinetic energy, you will take the work function to the other side, then bring maximum kinetic energy to this side, you will be able to find the work function for any, let's say, metals here. Sometimes you will be asked to find the threshold frequency given the energy or the frequency of the incident wave, let's say, and of course the maximum kinetic energy. You can do that. That is pretty simple. But something before we proceed, remember we said whenever its energy is given, let's say in electron volt, always convert it to joules. And of course, once they ask you to convert, let's say, joules, or give the energy in electron volt, once you have energy in joules, you'll divide by 1.6 times 10 to the power negative 19 to convert it back to back to electron volts here. So this is basically what we have. One thing, let me not forget here, sometimes instead of the frequency, the wavelength of the incident wavelength is given, the wavelength, yeah? So we do know that speed of light, it is equal to, or speed of the wave, that is basically, not this one here. Okay, so we can say speed of the wave, that is the speed of light, you can say it is basically the wavelength times the frequency. So if frequency is given, we can say frequency it is equal to speed of light over the wavelength. Then instead of this one, we can write Planck's constant. So if I use this one here, let's use a different color. We can say Planck's constant times, instead of writing frequency, we can write speed of light over the wavelength minus, that is Planck's constant, multiplied by threshold frequency. So of course we can use that as well. So whatever you're using, or you can say based on whatever that is given, of course you will use either this or the other equation here. Okay, moving on. So by the way, that is basically maximum kinetic energy. that is measured in joule because it is kinetic energy. Energy is also measured in joules. Planck's constant, it is this much, which you already know, that is joule second. F is basically the frequency, you can say, of the incident photon or the energy that is measured in hertz. And of course, F naught is the threshold frequency that is also measured in hertz here. Now, there was something also very important, which has been in Zhyar as well here, is this. Remember this. The equation suggests us, that equation, that the one that we have above, it suggests us that a linear relationship between the frequency and maximum kinetic energy, or you can say maximum kinetic energy. What do we mean by this? So don't we say maximum kinetic energy, it is equal to hf minus hf naught? All right, so you can see that there is a direct relationship between maximum kinetic energy and of course the energy as well. Can we say that? So we can say kinetic energy is directly proportional to the frequency of the incident wave or photon, you can say, yeah? So that is what we have. And then of course, there should be a linear relationship between frequency and kinetic energy or maximum, where, or you can say because h is Planck's constant or is a constant and the work function is h naught is basically the constant for any given metal, so that is a constant. So we can say that the slope of basically maximum kinetic energy and the frequency would give you the slope of that line, of course, it gives you the Planck's constant. Or you can say the slope of, let's say, the graph of maximum kinetic energy versus frequency would give you, for example, a slope, and that slope, of course, would equal to the Planck's constant, which is 6.63 times 10 to the power negative 34 joule second. And of course, you can see that this line is touching, let's say, the bottom, or let's say the ground or x-axis at a certain point. That certain point, of course, you can call it threshold frequency. That is basically the frequency or threshold frequency for, let's say, a certain metal here. So once again, if I draw this one here, this is maximum kinetic energy, yeah? And this is the frequency. So what would be the slope? Don't we say slope it is equal to rise over 1? Slope is rise over 1, or you can say y2 minus y1 extra, or let's just call it delta y over delta x. But what do we have on delta y here? That is basically, we can say maximum kinetic energy. What about on x-axis? We have frequency here. But look at this equation. Doesn't it remind you of, let's say, this equation right here? So we have maximum kinetic energy, let's say, that is maximum equals to hf minus, and of course, hf naught. If we assume that this is a constant, so we'll just leave this one behind for now, or you could just keep it as it is for now. So if we, for example, take these two parts right here, as you can tell here. So remember this, if I want to find or make h the subject here, that'll be equals to what? Or if we just like divide both sides here, only talking about this part here, that is basically, we get what? We get kinetic energy or maximum kinetic energy over the frequency that gives you the Planck's constant here. So we can say this is the same as the slope of the graph in here. So we can say the slope of the graph represents what? Represents the Planck's constant here. This is very important. And the point where the line touches the ground or x-axis, that is the intercepting x-axis, that'll be basically, you can call it, this is the threshold frequency. So this graph shows a linear relationship between the maximum kinetic energy and the emitted electrons and the frequency of the incoming light. The intercept with the horizontal axis, that is the threshold frequency, and we're talking about this one here. T4 threshold frequency here. Okay, now this is something also very important here. It says, when does the photoelectric effect occur, let's say, occur according to Einstein's equation? So basically, we've learned about Einstein's equation. So when does the photoelectric effect occur according to Einstein's equation here? So we'll say photoelectric effect occurs if, remember this, that is if the frequency of, let's say, if the frequency of the incident photon, it is bigger or equal to the threshold frequency. If it is bigger than the threshold frequency, of course, the electrons will be extracted at some speed. We can find the kinetic energy for that, let's say, electron as well. But what happens if, let's say, if the frequency of the incident wave, it is equal to the frequency or the threshold frequency? In that case, electrons will be extracted, don't forget, will be extracted, but at a zero kinetic energy. So you might say, how is it possible? It is possible. Electrons will be extracted, but at zero kinetic energy, almost like at zero speed, you can say. That is one thing, yeah? What happens if the threshold, if the frequency of the incident, what happens if the frequency of the incident photon is less than the threshold frequency? Then in that case, no electron will be extracted no matter how intense the light is. So it doesn't depend on the intensity, don't forget, which is unlike what classical physics said, it depends on the frequency. So even if we have very low energy, if the frequency is equal or above the threshold frequency, then electrons would be extracted or removed immediately. Okay, or instantly, you can say. So this is what we have. Photoelectric effect occurs when the energy of the incident photon, HF, is greater than or equal to the work function here of the metal. So you can say it is equal, greater than, or equal to. What about if it is smaller? Of course, electrons will not be extracted regardless to the intensity. So we'll say if HF is smaller, photoelectric effect does not take place. What if it is equal to, if the incident frequency of the incident photon is equal to the threshold frequency? We've said that the electrons will be ejected, but with zero kinetic energy. Okay, so another question, what does the maximum kinetic energy of a photon ejected from a surface depends on? So based on this, of course, we'll say it depends on two things. It depends on the work function and also depends on the frequency of the incoming photon here. Didn't we say that maximum kinetic energy, it is the difference between the two here? So we'll say maximum kinetic energy. It is basically, that is HF minus HF naught, yeah? So basically we said this is the energy, or you can more specifically, you can say the frequency of the incident wave here. That is the frequency of the incident wave, and this is the threshold frequency here, yeah? So it depends on these two things here. Okay, that is maximum kinetic energy, depends on this two things, or you can say it is the difference between the frequency of the incident wave or photon and also the threshold frequency of the surface or of the metal in general. Okay, so that is the answer to that question here. Now we have another question, says, which has more energy, a photon of ultraviolet radiation or a photon of yellow light here? Now, in order to answer this question, you will have to know which one has a higher frequency. Remember this, we have ultraviolet radiation and yellow light. And of course, when we say ultraviolet, you will have to know the electromagnetic, let's say, spectrum. That is basically, we can say radio waves, microwaves, let's say, let's use the other letter for micro just to help you remember this. We can just write M for that. Okay, let's just call it microwave here. And then we have infrared, okay? And then, of course, we have visible, and then we have ultraviolet, you can call it UV, and then we have X-ray, and of course, we have gamma rays as well, okay? Now, for visible light, of course, we have, you can say for visible light, we have all the visible colors, and that is, we can call it ROY, G, B, I, V, yeah? That is red, orange, yellow, green, blue, indigo, violet here. So what are the wavelength or the frequencies that we have? It says a photon of ultraviolet radiation. Photon of ultraviolet radiation is right here. What about the other photon here? It is a yellow light, yeah? So here's yellow light, you can see, yeah? So of course, as we go from radio to gamma ray, the frequency increases. So can I say the frequency of ultraviolet radiation is higher than the frequency of yellow light? If your answer is yes, then of course, congratulations, you're correct. Well done, okay? So we said that. So the question says, which one has more energy here? So, of course, energy, it is equal to what? Energy, it is equal to HF, yeah? So that means this is constant. That's Planck's constant. The higher the frequency, the higher the energy, yeah? So which one of these two frequencies will have a higher energy? That is, of course, for the energy for ultraviolet, or let's say for ultraviolet radiation, yeah? Well done. That is how you can do that. Make sure that you know, like, the frequency that is given, what category, what type of electromagnetic wave it is. Then based on the range, is it a frequency with a, or you can say high frequency or low frequency. Based on that, you can compare which one has more energy. The one with a higher frequency normally would have a higher energy. Okay, so clearly the photon of ultraviolet radiation. Now we have another question, says if the photoelectric effect is observed for one metal, all right, using the light of a certain wavelength, okay, can you conclude that the effect will also be observed for another metal under the same condition? We'll say no. Why? Because different metals, of course, may have or will have, let's say, different work function. So maybe the work function for the other metal is bigger than let's say the frequency or the threshold frequency for the other metal is bigger than the frequency of this incident light, in that case, no photoelectric effect will take place or no electron will be ejected. So not necessarily when photoelectric effect takes place for one metal, we can say that it happens for other metals as well because they have different work function, or you can say they have different threshold frequency. Okay, so the answer is no, because other metal may have a larger work function. Another question says, what effect, if any, would you expect the temperature of a material to have on the ease with which electrons can be ejected from one metal in the photoelectric effect? Normally, once you increase the temperature, let's say, of course, that helps, let's say, the metals or the particles of the metal will have more energy. So having more energy, let's say, makes it a little bit easier for the electrons to extract, let's say, less, because with a little bit more of energy, or let's say with a little bit of more frequency, let's say, then of course these electrons will be ejected. So once again, let's make it short. We'll say temperature or higher temperature will make it easier for electrons to be ejected, and that's it. You don't have to complicate it. So it says, which one of these four photons has more energy? A photon of, is it infrared radiation, yellow light, visible light, or red light? Yeah? So take a look here. We have infrared radiation, that is one of the electromagnetic wave, and of course we have a visible color spectrum, so you can say, yeah. So we have infrared, that is before the visible light, right? Visible light. In visible light, we have, let's say, a Roy G-BIV, we can say, yeah. So now we have infrared, that is below the visible, so clearly this one will not have the highest energy. And then what are the other colors? We have yellow, violet, and red, yeah? So yellow, violet, red. You can see here red is among the visible colors would have the least energy. And then you can say yellow comes a little bit higher than that. And then, but we have violet here. So violet is at the other end, or you can say with the highest frequency. The higher the frequency, the more the energy. So of course we can say it is violet light. Okay, now another question here says, take a look, says the graph to the right shows a linear relationship between maximum kinetic energy and also the energy of, let's say, of the emitted electrons and the frequency of the incoming light in the photoelectric effect. What is straight line slope representing here? We can say the slope of this straight line here, of course, we said, if you remember, it represents what? It represents the Planck's constant. But again, why? Because when you find the slope here, let's say the slope, right? The slope, that is basically, it is equal to y, delta y, you can say over delta x, that is obviously, or you can say rise over 1, that is basically maximum kinetic energy, right? Over what? Over the frequency, yeah? And of course we said this one, it is equal to what? Equal to Planck's constant. So which one it is? We can say it is option B here. Okay, and then where the line touches the, or the intercept with the x-axis, we said that is the threshold frequency. Now let's get into some questions and make it more interesting. We have a question that says, light of frequency of 1 times 10 to the power 15 hertz illuminates a sodium surface. The ejected photons are found to have maximum kinetic energy of 1.78 electron volt. Don't forget, we have electron volt. Are we going to use electron volt? The answer is no. You'll have to convert this one to joules. And how do we do that? By multiplying by 1.6 times 10 to the power negative 19. The question says, find the threshold frequency for this metal. How do you find the threshold frequency? It is easy enough. Just bear with me and let's do this together. All right, so the first thing that we have, we'll have to convert these electron volts into joules here. So what are the information here? Remember, we have the frequency of the light, that is F, which is 1.00, or let's just call it 1 for now, times 10 to the power 15 hertz. Okay, that is basically in hertz. And then we have the maximum kinetic energy. So we have kinetic energy max, right? It is, we said it is 1.78 electron volt, but we're not going to use electron volt. So we'll say 1.7 times 1.6 each electron volt. Remember, each electron, or you can say the charge of electron 1.6 times 10 to the power negative 19, yeah? You do know this one. Then, of course, by doing this, you will be converting electron volt to joules. And then next, it says, find the threshold frequency. So how do we find the threshold frequency? We'll have to get a calculator and find this value in joule, and after that we're going to do that there. All right, let's use a thicker line here. Okay, so now we do know that maximum kinetic energy, it is equal to what? This is maximum. It is equal to energy, or you can say HF minus HF naught. That is the threshold frequency. We want this threshold frequency, correct? So now, of course, we're going to, remember, this is negative. We're going to take it to the other side, becomes positive, and this is positive. We take to this place, it becomes negative. So we'll say threshold frequency and all that, or work function, it is equal to the energy, let's say, minus maximum kinetic energy. Right? This is maximum, but we want threshold frequency, not the work function entirely, right? And in that case, of course, it is equal to threshold frequency, it is equal to HF minus kinetic energy max over the Planck's constant. Now let's plug in some numbers. All right, so let's find out, remember, maximum kinetic energy has to be in joules, and then after that we can plug it into the equation using, of course, or doing the math, we can find the threshold frequency here. Okay, so of course, after getting a calculator here, now we can start with this, or just multiply this one so that you can get the energy here. So let's start with this. So we'll say 1.7, remember this, multiplied by 1.6 times 10 to the power negative 19. Then, of course, we will get 2.72 here, okay? Let's just double check with this one more time. We have, by the way, this is, remember this, 1.78 electron volt. I think I did not write 8 because that would have, of course, it would affect this one here. So let's write 1.78, and then that is electron volt. So we'll have to write the 8 here so that to get the correct answer. We'll say 1.78 multiplied by 1.6 times 10 to the power negative 19. That is, of course, 2.848 times 10 to the power negative 19. We can round it up, of course, to 2.85 if we want to. Okay, multiplied by 10 to the power negative 19 here. That is going to be in joules, don't forget it. Now we're going to plug in this number into the equation here. So we will say, we'll have to write it small so that we can have enough space. So now Planck's constant, that is 6.63 times 10 to the power negative 34. All right, help me continue with this. Multiply by the frequency that we have, which is 1 times 10 to the power 15 hertz, not multiply. Then, of course, minus, that is the energy we have. You can put it in a bracket so that you don't get confused, or you get it so that you don't make mistakes while you're calculating this. And then minus the kinetic energy. We said the kinetic energy that we have, it is 2.85 multiplied by 10 to the power negative 19, that is joules, divided by Planck's constant. Let's see if we can erase this one. This Planck's constant is too big in here. Okay, so let's make this one smaller. That's h, and then divide by 6.63 multiplied by 10 to the power negative 34 joule second. So you do the math, of course, you'll be able to get the threshold frequency here. So let's do the math. This is one of the reasons I don't like to do the math like while I'm doing this, because it is really time consuming. It would be best if we just look at the calculation, see what it is, and tell you this is the answer. But I'll just do it once. Next time I'll just go ahead and use the answer that we have on the board. Okay, so let's begin with this. 6.63, you can do it with me. Just to double check with the answer, 6.63 times 10 to the power negative 34, and then of course multiplied by what? By 1 times 10 to the power 15, right? Then of course now you can close brackets, and then we'll say minus the maximum kinetic energy, which is 2.85 by rounding, times 10 to the power that is negative 19. We can close bracket and then divide it by Planck's constant, which is 6.63 times 10 to the power negative 34. And then of course, okay, got a math error. Perhaps I've done something incorrect. Let me do it separately. 6.63 times 10 to the power negative 34. Okay, and then multiply by times 10 to the power 15 hertz. And of course we get 6.63 times 10 to the power negative 19. Then minus, you can open bracket, 2.85 times 10 to the power negative 19. Then close bracket. That is 3.78 times 10 to the power negative 19 divided by Planck's constant. That is 6.63 times 10 to the power negative 34. Close bracket again, of course, we will get 5.7, right, times 10 to the power 14 here. So we can say the threshold frequency, if we write it here, we'll say threshold frequency, it is equal to 5.7, of course 7014, but we're not going to write it, times 10 to the power 14, that is going to be hertz here. Okay, this is what we have basically. So if you take a look, for example, at this tree here, I have 5.7 times 10 to the power 14 here, while the incident frequency here, it is 1 times 10 to the power 15, which is bigger than this. Of course, it is able to extract electrons from the surface of the metal here. Okay, so of course you can say this is the answer there. Okay, so we can say all the other questions are very similar to this, very, very similar, yeah? But of course, just let's say a matter of different numbers. Otherwise, all the other information, you can say it's the same procedure. So let's take a look at this one here. It says, in the photoelectric effect, it is found that the incident photon with energy, so this is the incident photon energy, the energy of the incident, let's say photon, it is 5 electron volt, but once again, convert this electron volt into joules, and how do we convert that? By multiplying this one, take a look, this is the value of an electron, yeah? Which is multiplied by 1.6 times 10 to the power negative 19, negative 19. So negative 19, right, you will be converting electron volt to joules now, and then we'll produce an electron with maximum kinetic energy. So we have kinetic energy, maximum, that is an electron volt again, one more time, let's say times 1 times, or 1.6 multiplied by 1.6 times 10 to the power negative 19, you will convert the electron volt to joule again. It says, what is the threshold frequency of this material here? One more time, like we've done this one before, so it is the same procedure, yeah? You'll just say threshold frequency equal to energy minus maximum kinetic energy over the Planck's constant. The energy that we have is written or given right away, so you don't have to say h times the frequency of the incident photon. No need for this because the energy is already given, which is 5 electron volt, convert to joule. You'll write it here. Maximum kinetic energy converted to joule and write it here, and then divide by Planck's constant. Of course, you will find the threshold frequency here. Okay, going to another question. Or question says, light of wavelength 350 nanometer falls on a potassium surface, and the photoelectrons have a maximum kinetic energy of 1.3 electron volt. What is the work function of the potassium, and what is the threshold frequency of the potassium as well, or potassium? All right, so let's solve this question here, because there is a slight, let's say, difference idea in this, which I can't say it is a big deal of an idea or whatever, but we'll do this one here. So the first thing that we have, it is the wavelength instead of giving you the energy or the frequency. That is 350, remember this is nanometer. And of course, immediately if we convert nanometer to meter, we'll say 350 times 10 to the power, how much is a nano? Nano, so that is 9, yeah? Very, very good. In meters, you can say this much, yeah? And then what else do we have? It says maximum kinetic energy. So kinetic energy maximum here, it is clearly 1.3 electron volt. But once again, 1.3 times 1.6 times 10 to the power negative 19. That'll be into, we can say joules, yeah? So whatever the answer is, you could just find it in joules in here. Then the question says, what is the work function of the potassium, yeah? So of course we have this. We'll say maximum kinetic energy. Let's say if that is the first one, maximum, it is equal to what? It is equal to the energy that we have minus what? Minus the work function, you can say. If not, you could just go, for example, ahead with HF, that is the energy of the incident photon, you can say minus the work function, which is HF naught. But we don't have the frequency there, by the way. And we've already learned that regarding this one, C, it is equal to frequency times the wavelength, yeah? So frequency, it is equal to speed of light over the wavelength. So now I can substitute this into the equation. It becomes what? It becomes H, we can say C over the wavelength minus the work function here. So now we're trying to find this one here, and this is the kinetic energy or maximum kinetic energy. So we'll say the work function, it is equal to hc over lambda minus maximum kinetic energy. All you have to do now is plug in the numbers. Once you do, of course, you're going to find the work function here. So this is the work function, but this work function that you're going to find, it will be in joules. So the question next says, or the second part says, what is the threshold frequency of the potassium or potassium? So now you have the energy. So if you want to find the threshold frequency, now of course you can say threshold frequency, it is equal to, that'll be F naught, yeah? Whatever the energy that you found in joules divided by Planck's constant, you'll find the threshold frequency. And that is all the idea in this question. There's nothing much or more. By the way, if they ever ask you to find the threshold frequency in electron volt, what would you do or what have you done in that case? Of course, that is in joules, yeah? If you want to convert joules to electron volts, we normally divide by 1.6 times 10 to the power negative 19, then we will be able to convert from joules into electron volt. Okay. All right, now another question here says, calculate the work function of sodium using the information given in sample problem 8b. So if these are the information given here, that is the frequency of incident photon, that is maximum kinetic energy in electron volt, don't forget you'll have to convert, and then Planck's constant at this much, can you find the threshold frequency? That is the same as the other question, nothing much of a big deal. All right, take a look at this one here. This is also something interesting, especially for multiple choices maybe. It says, which of the following metals will exhibit the photoelectric effect when a light of this much hertz, let's say frequency, is shined on it? So remember this, that means the frequency, or you can say the incident frequency, it is what? It is 7.0 times 10 to the power 14 hertz. That is the incident frequency. So how do we know whether this frequency will extract electrons from the surface of these metals or not? While we're given the threshold frequency of each one of these metals here. So how do we do that? One way, or one easy way, is this. By finding the threshold frequency and comparing it to that frequency. If this frequency, of the frequency of the incident light or photon, if it is bigger than the threshold frequency of these metals, then of course it will be able to extract electrons from the surface. If that frequency is smaller than the threshold frequency, then it will not be able to extract electrons from the surface. So how do we do that? Let's just go ahead through this one. I'll do one of them, you could do the rest on your own here, yeah? So let's say the first one here, we have lithium, yeah? That is, we have the work function, which is basically 2.3 but electron volt. You will have to use or convert this one to joules by multiplying 2.3 times 1.6 times 10 to the power negative 19, so that you will be converting electron volt to joules. That is the first thing. Once you do that, we have to find the threshold frequency. Threshold frequency, it is equal to this energy that you found, 2.3 times 1.6, whatever the energy is, times 10 to the power negative 19, divided by Planck's constant here. Correct? Once you do this, of course, you will find the threshold frequency in hertz here. Now you can compare these two different frequencies together. If the frequency of the incident light is bigger than the threshold frequency, that means electrons will be ejected from the lithium surface. All right? And of course, the answer that we get, this is bigger than this, of course, electron will be ejected from lithium surface here. And then, of course, you will do the same thing with the second metal, which is silver. You can tell that, for example, after converting this one to joule, you'll find the threshold frequency using the same procedure. You'll find out that the threshold frequency is bigger than the incident frequency. That means electrons will not be ejected from silver surface. What about cesium here? You'll see that that frequency, it is bigger, or you'll find out that it is bigger than the threshold frequency. Then, of course, electrons will be ejected here. So you can see here, after, let's say, doing the math, you will see that this is the threshold frequency for lithium, which is 5.55 times 10 to the power negative 14, while the incident photon is 7 times 10 to the power 14. So 7 is bigger than 5, so electron will be ejected. 7 is smaller than 11, electron will not be ejected. Considering these are of the same power, so will not consider that. And of course, what about this one? 7 is bigger than 5. That is for cesium. Electron will be ejected. Now, photoelectric, you can say, effect occurs for both lithium and cesium because the incident energy, or you can say frequency, it is bigger than the threshold frequency. Okay, now this is another situation where you have to find the threshold frequency. But once again, we have the frequency, maximum kinetic energy in electron volt converted to joule. Then you could do the math, which is the same as the previous one here. Okay, now this is one of the easiest question here. It says just the application of the equation. It says the threshold or the threshold frequency of silver is this much. What is the work function? Yeah. So remember, we have the work function normally equals to what? You can write the work function as like in words, or you could just give it this symbol here. That is basically threshold frequency, or let's say Planck's constant first, makes no difference. Planck's constant times threshold frequency. You're given this. You know Planck's constant, so you multiply the two, you get the work function, of course, yeah? So, but remember, that work function you find it is in joules, don't forget. What if they ask you to find the work function, but in electron volt? Then you will divide by 1.6, whatever the work function is, divide by 1.6 times 10 to the power negative 19, that'll be in electron volts, okay? That'll be the work function for silver. Okay, now take a look at this one here. This is also an interesting question. It says what? It says a light source of wavelength lambda, so we don't know what lambda is exactly. It says illuminates a metal and ejects photoelectrons with a maximum kinetic energy of 1 electron volt. Don't forget, that is an electron volt converted to joule. We have a second light source of wavelength, or you can say of wave energy, which is the wavelength of the second wave is half of the wavelength of the first one here, okay? It says eject this photoelectron with a maximum kinetic energy of 4 electron volts. Don't forget, what is the work function of the metal here? So since it is the same metal, can we say if it is the same metal, the work function, it is the same for both materials, yeah? Yes, well done, very good. So if that is the case, let's solve this one together, yeah? By the way, this is pretty easy, but of course there is only one idea in this. Because it is the same material, that means they have the same work function. If that is the case, we will kind of like equalize both, let's say, both wavelengths here so that we can find the wavelength. Knowing the wavelength allows us to find the work function for the metal here. Okay, so let's see how we do this, yeah? So remember, now normally we have maximum kinetic energy because we can say, this is what we have. Let's say the first one, maximum kinetic energy, that is, let's say for the first wavelength, it is equal to HF minus the work function here, which is basically HF naught here. This is the work function, correct? Now I can, of course, we can make this one the subject here. So we'll say work function, it is equal to HF minus what? We can say minus HF, right? Minus, we can say, maximum kinetic energy here. That is, let's call this one the first equation. And then for the second one here, of course, we have the second, you can call it the, if you want it, you can call it the first or the second, it doesn't matter here. So now we have, for the second time, we can say a second light wave here, maximum kinetic energy, it is equal to, once again, the energy of the incident photon here minus the work function here. Once again, since it is the same metal, so they have the same work function. If you want to find the work function, it is equal to the energy of the incident photon. That is going to be for the second one, you can say. And then, of course, divide minus the maximum kinetic energy here. That is, you can say, for the second one here, maximum. So this is the second equation. Now, like I said, because this two is the same metal, so they have the same work function. If they have the same work function, that means these two are equal. If these two are equal, can I say these two are equal as well? The answer is yes. So what do? I'll equalize, you can say, both equations. So I'll say the first one, HF, right, minus maximum kinetic energy. Kinetic energy maximum. That is for the first one. It is, let's call it just 1 on 1, equals to HF, let's call it 2, minus maximum kinetic energy. Let's say this is the second maximum kinetic energy. But as you can tell here, I don't have the frequency, but instead of the frequency, I'll have something else. I'll have the wavelength, yeah? So we'll say h times, what is the frequency equal to? Speed of light divided by what? Divide by the wavelength, and then minus, what is the kinetic energy for the first one, yeah? Maximum kinetic energy, it is in 1 electron volt. By the way, I'll just keep it in electron volt for now. I can do the conversion later. Equals to the other one again, it is equal to h, but remember this. That is speed over wavelength, yeah? But it says the wavelength is what? Is 1/2 of the other wavelength. So can I say it is 1/2 of the wavelength minus the kinetic energy, which is 4 electron volt minus this. So this, of course, goes up. So if I do this one more time, that is hc over wavelength. You can call it 1 minus 1. It is equal to, this is going to be 1 as well here. We can say hc, I think, I don't have enough space, hc. By the way, this 2 goes up, becomes 2hc over the wavelength here, minus 4. So of course, numbers to one side, these are to the other side here. So this is 2, yeah? So we're going to move this 2 to the other side. This is, or you could just bring this one here because this is positive and bigger. We'll move this one to the other side, and this bring this 4 here. So it becomes what? Becomes 2. I think I should, let me just write it up a little here. Okay, I hope it is not too much. Okay, so we'll say 2hc over lambda minus hc over lambda, it is equal to 4 minus 1. Okay, so of course it is going to be hc over lambda, because 2 minus 1, that is 1 obviously, it is equal to 3 electron volts here. Remember this, yeah? So now I can plug these back into the equation if I want to, let's say. If not, if you remember here now, hc minus lambda is equal to 3 electron volt. But if we go back to the other one here, like, do you remember or recall the equation that we used here? So now I have 3 electron volt. Okay, so if we go back to the main equation that we wrote, as you can tell, one of the equations that we have, we said hf, that is the work function, yeah? And of course, we said that this one here, using, of course, the frequency, this is what I wrote, hc over the wavelength minus 1, yeah? Because the kinetic energy for the first one was 1. Now we have found this one, hc over the wavelength here. So, and this is 3 electron volt, correct? Minus 1 electron volt, of course, we get a result of 2 electron volts. So we'll say the work function for this metal is basically, it is 2 electron volt, but that is in electron volt. If they ask for the work function in joules, you'll have to convert this one into joules here. Okay, so that is basically the first part. Let's say if, so this is how you would normally do that. What is the, or do we have, what is the work function of the metal? So you would just find that way, this way, yeah? Now, there was another question that perhaps I've kind of like mixed with the other question. Normally, they'll ask for, let's just say, what if they were asking for the threshold frequency in that case? So knowing this one here, let's go back to this one. If they were asking for threshold frequency, then of course, using that one, if they were asking for threshold frequency, if I go back to this one here, then of course, you need to use or convert this one into joules by multiplying by 1.6 times 10 to the power negative 19, then you will find the answer in joules here. So whatever the answer is going to be in joules. But then, that is threshold frequency, yeah? And then of course we would say, I mean the work function here. If we want to find threshold frequency, we'll say this energy in joules, don't forget, divided by Planck's constant, we'll find the threshold frequency for this one. Of course it is in hertz here. So we'll have to divide or convert to joule first, then we can find the frequency. And that was the answer to this question here. All right, we'll end up right at this point here. Don't forget, this is basically what we have, and these are some mosaic questions which I really want you to go through because these are very important. Next lesson, inshallah, we'll go through photon theory and photoelectric effect. We'll explain this a little bit more, and hopefully we can go to a new concept. Till then, keep practicing. And I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.